Today I'm going to talk about the monitoring and assessment of a prestressed concrete segmental box-girder bridge. This is the planned presentation. I'm going to talk about bridge description, observed behavior and context, instrumentation for SHM, finite element model, model analysis, load tests, and some data analysis that we done on the bridge for model analysis, load tests, and SHM. And then, if I have time, some conclusions. The bridge description, there were two twin bridges that were built at the same time in 1964. They were located on Highway 15 to Mont-Tremblant ski station, for those who know the area, over the Rivière of Millet. They were continuous, three-span, prestressed concrete box-girder bridge with variable inertia. At the time of their construction, they were the first structure of this type in North America to use a European method of building successive cantilevers without scaffolding. In this presentation, we're going to talk about the northbound bridge. The southbound bridge was monitored by us from 2002 until its replacement in 2006. So you have here bridge description. So you have side span that are 40-meter length here, and you have the central span, which is 80 meters. You also have a single span here, which will not be discussed in the presentation. Here you have a cross-section of the bridge. You see around 40 feet wide for two traffic lanes over the bridge. Observed behavior and context. Most prestressed, probably as you know, most prestressed concrete box-girder bridge built before 1985 have developed structural problems through their useful life. Only a few years after opening, both bridges began to sag much more than anticipated. Original design did not meet the recommended span-to-deep ratio for those bridges. Structural disorders have been noticed over the years, such as vertical cracks in the web of each end segment, diagonal cracks in the web near the key segment, and longitudinal cracks at the junction of the top flange and the webs. The original design underestimated live load effect, pre-stress losses, temperature effects, and effects of delayed concrete deformation, shrinkage, and creep. To overcome this deficiency, major reinforcement work was carried out in summer of '98. Horizontal and vertical pre-stressing tendons were added at some place on the bridge. The instrumentation for structural health monitoring. On this bridge, SHM was initiated in 2004 to follow the progression of the mid-span vertical deflection and to collect information relevant to the management of the structure. Only slowly progressive failure modes can be properly monitored. In fall of 2012, the Ministry Authority mandated us to determine if the bridge could be replaced, if the bridge replacement could be delayed by at least 5 years. Initially, it was planned for 2013. But they asked us if he could delay so they can spend money on other bridge. Careful analysis of the data gathered after 8 years of SHM revealed that the bridge replacement could be delayed for a few years. So you have the sensor location for the SHM. The blue square are the rotation that was installed inside the box girder. They were used mainly to calculate vertical deflection. Then you have also the light square, which are the rotation at the top of the pier. We also measure the displacement at the support. The fixed support is at that pier, and you have a mobile here. We also have a gravity wire deformation sensor, a few sections, top and bottom of each web. And we have telescopic extensometer. They are 6 meters long, and they integrate all deformation between the two anchor points. And we also have a temperature section at 50 meters from the beginning of the bridge. We also have a finite element model. As you can see here, it was built with using plate element, and it was calibrated with the help of model analysis data, vibration frequency, and measure from SHM. Model analysis, over the years, we've done 6 model analysis on the bridge. In the fall of 2004, 6, 9, 11, 14, and 16. All the tests were done under ambient traffic conditions. We also did 3 load tests on the bridge. They were static load tests. They have been carried out on 2004, 13, and 16. For those tests, we were using semi-trailer trucks of 40 tons, which is 88 kips. We have 3 longitudinal paths that have been considered. So just to show you those. We have path A, which is 2 feet from the curb, and you have the 2 trucks, one behind each other and at the center. You have path C, which is the same thing, but on the other side, 2 feet again for the curb. And then with 2 trucks, we have what we call path EC, which is one on each side, and the nose is just at the center of the bridge. Here are some results from the model analysis. You have here the different mode shape that we been able to see. You have the prediction from the finite element model. You have the average temperature at the time that we done the model analysis. And as you can see, what we would like to highlight this morning is that fact that higher modes, we saw some change in the frequency from the model analysis from 2014 to 16. So we have a decrease in those values. This is what we would like to highlight here. Some results from the load test. Here is the vertical deflection at midspan. So you have the finite element model prediction, and this is with path EC, so 2 tracks on each side of the bridge. You have the 2013 result, which is almost 16 millimeters, and as you can see in 2016, we have 2 millimeters more for the same condition and same load conditions. There is a lot of stock in this figure, so I'm going to try to make something good. You have the maximum stress at midspan. So section 79 is close to midspan. It's in the center of the bridge, which is 80 meters. And you have here path A, path C, and path EC, and you have all the different load tests that we've done, 2004, 13, and 16. You have the condition with trucks on decks and the final record, which when was the truck was leaving the deck and there was no load on the deck. The light color are the prediction from the finite element model without bearing restraint, cracks, or modulus reduction. So just a few things. You can see that the stress measured in the damaged bridge are lower than the original prediction, and stress in 2016 are much higher than those of 2004 and 2013. There is much more in the article, but since I have not much time left, I'm going to stay to that. Now we get into the SHM result. Here you have some result from the displacement at the support. So you have displacement at support A, which is the blue line. You have the displacement, relative displacement at the axis, which is the orange. So as you can see, they move with the temperature, which is in gray in the back. And I do remember you that this one is fixed. And we were anticipated to see some displacement over here, but as you can see, the green line, there was no displacement. So instead of a mobile, it was in real fixed. So if we look into the rotation at the top of the pier, as you can, the B axis is in blue and the C axis is in green. So as you can see, we do have a permanent rotation over the pier, and they move with temperature, and then with around 2000, it's really small even for me, 2014 and 15, we can see that both are going away from each other. This indicates us that the vertical deflection at midspan is pushing the top of the pier away from each other. Here you have results from the finite element model with bridge deformation with low internal temperature and with high internal temperature. So you can see how the pier are moving with high and low temperature. Here are the results for the telescopic instantometer, the long base sensor. This is raw data. So as you can see, most of them are moving between 0 and 3 millimeters. but we have some sensors which are 6 meters long that integrate all the deformation, cracks, and everything that's between the anchor point. So you can see at 115 meters, just over the pier here at the top, in red, that during the winter, with temperature is low in gray, that cracks are opening. Same thing at the end for section 35 here. We have some cracks that are opening during winter, and during the summer, all cracks are closed, and those sensors give us the same result as all the most of them. We also have a transverse rotation at midspan. So as we can see, you have a permanent transverse rotation over the time, and the red square here indicate us that something came up in the spring of 2015. We call it in the paper an event. So an event occurred, and after that we got a permanent transverse rotation at midspan. Here you have the vertical deflection. It's coming from the rotation sensor over the time. So as you can see, you have when we give the OK in 2012 to continue the operation of the bridge, we have a good agreement, a stable vertical deflection, and then with the time we get more and more vertical deflection at midspan of the central span. These are longitudinal stress calculated from vibrating wire sensor. Section 42 is near, those values are on the top of the web, east and west web, so near one of the pier, and section 118 is the opposite pier. So as you can see, a stable movement, and then suddenly in 2015, something came up at section 42. And same thing for section 118. Here you have the stress at section 79, which is at in the southern span at midspan. So as you can see, over the time, they were both increasing at the same rate, and then something came up in the spring in 2015, and the behavior changed a little bit, and then they are moving again with stresses. Is rising again at the same rate, but something came up in 2015. So now the conclusion. The SHM program implemented for this bridge allowed the request 5-year delay for the bridge replacement. Damage on the bridge was observed during the last year of SHM. Higher order mode frequency were reduced. Stress increased over the pier and at the midspan from load tests 2013 to 2016. We have a slow and progressive permanent midspan deflection, which is increasing, and an event appeared at the end of April 2015. We have a permanent girder transverse rotation that has been detected at midspan. We have an axial force that has been developed in central span between B and C axis in combination with a permanent and progressive rotation at the top of these piers. Telescopic extensometer or long base sensor indicate complete pre-stressing loss in the vicinity of some cracks at low temperature. Breathing cracks and concrete decompression cause larger stress in pre-stressed tendons. This phenomenon promotes premature failure of tendons, especially those located in the top flange with its corrosion-friendly arrangement. Note that the diagnosis has been achieved with the help of SHM data and no total applied load stress measurement. And finally, this is the bridge at last summer. So we would like to thank the people that work with us on this project. Thank you very much.